Welcome to Module 2, Machine Learning and Mahout. Hadoop has potential to replace the Enterprise Data Warehouse, or EDW. Hadoop has an ability to store and process massive amounts of data using commodity hardware that scales extremely well and at a very low cost. Hadoop is good for batch-oriented work, not very good at OLTP workloads. In this module, we're going to learn about the basics of machine learning, followed by an in-depth look at Mahout, a machine learning library for Hadoop. We'll have a very interesting demo on Mahout at the end of this module, just to make sure you understand. So, let's begin. Now it's time to start the first lesson of the module, Basics of Machine Learning. In this lesson, we're going to learn all about machine learning and its underlying principles. In this lesson, you're going to see an introduction to machine learning, and you're going to learn the basics of machine learning. Let's begin. Machine Learning Introduction. Machine learning, a branch of artificial intelligence, concerns the construction and study of systems that can learn from data. For example, a machine learning system could be trained on email messages to learn to distinguish between spam and non-spam messages. After learning, it can then be used to classify new email messages into spam and non-spam folders. The core of machine learning deals with representation and generalization. Representation of data instances and functions evaluated on these instances are part of all machine learning systems. Generalization is the property that the system will perform well on unseen data instances. The conditions under which this can be guaranteed are a key object of study in the subfield of computational learning theory. There's a wide variety of machine learning tasks and successful applications. Optical character recognition, in which printed characters are recognized automatically based on previous examples. It's a classic example of machine learning. Machine learning is a complex discipline, and lots of research is going on about it. Machine learning is the science of getting computers to act without being explicitly programmed. In the past decade, machine learning has given us self-driving cars, practical speech recognition, effective web searching, and a vastly improved understanding of the human genome. Machine learning is so pervasive today that you probably use it a dozen times a day without even knowing it. Many researchers also think it's the best way to make progress towards human-level AIs. In this module, you're going to learn about the most effective machine learning techniques and gain practice implementing them and getting them to work for yourself. More importantly, you'll learn about not only the theoretical underpinnings of learning, but also gain the practical know-how needed to quickly and powerfully apply these techniques to new problems. Finally, you'll learn about some of the Silicon Valley's best practices in innovation as it pertains to machine learning and AI. Machine learning concept. Let's clarify what comes under machine learning and what can be classified as machine learning. Most programs tell computers exactly what to do, such as database transactions and queries, controllers for phone systems, manufacturing processes, transport, weaponry, etc., media delivery, simple searching, social systems, chat, blogs, email, etc. These are not machine learning. So the question is, what exactly is machine learning? Well, it's an alternative technique. It's having computers learn what to do. Machine learning refers to a few classes of programs that leverage collected data to drive future program behavior. This represents another major opportunity to gain value from data. In 1959, Arthur Samuel defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. Tom M. Mitchell provided a widely quoted, more formal definition. A computer program is said to learn from experience E with respect to some class of task T and performance measures P, if its performance at task in T as measured by P improves with experience E. This definition is notable for its defining machine learning in fundamentally operational rather than cognitive terms, thus following Alan Turing's proposal in Turing's paper, Computing Machinery and Intelligence, that the question, "Can machines think?" be replaced with the question, "Can machines do what we, as thinking entities, can do?" These two terms are commonly confused, as they often employ the same methods and overlap significantly. They can be roughly defined as follows. Machine learning focuses on prediction based on known properties learned from the training data. Data mining focuses on the discovery of previously unknown properties in the data. This is the analysis step of knowledge discovery in databases. The two areas overlap in many ways. Data mining uses many machine learning methods, but often with a slightly different goal in mind. On the other hand, machine learning also employs data mining methods as unsupervised learning, or as a pre-processing step to improve learning accuracy. Much of the confusion between these two research communities, which do often have separate conferences and separate journals, ECML PKDD being a major exception, comes from the basic assumptions they work with. In machine learning, performance is usually evaluated with respect to the ability to reproduce known knowledge, while in knowledge discovery and data mining, or KDD, the key task is the discovery of previously unknown knowledge. Evaluated with respect to known knowledge, an uninformed or unsupervised method will easily be outperformed by supervised methods, while in a typical KDD task, supervised methods cannot be used due to the unavailability of training data. The 3 C's. Machine learning is an active area of research and new applications. There are 3 well-established categories of techniques for exploiting data: collaborative filtering, recommendations, clustering, and classification. Collaborative filtering. Collaborative filtering is a technique for recommendations. Example application. A group of people like certain books. Based on this, they learn to suggest what someone may like based on what they already like. This is a very useful technique. It helps users to navigate data by expanding to topics that have an affinity with their established interest. Collaborative filtering algorithms are agnostic to the different types of data items involved, so they are equally useful in many different domains. Collaborative filtering, or CF, is a technique used by some recommender systems. Collaborative filtering has 2 senses, a more general one and a narrow one. Click on each tab to learn more. In general, collaborative filtering is the process of filtering for information or patterns using techniques involving collaboration among multiple agents, viewpoints, data sources, etc. Applications of collaborative filtering typically involve very large data sets. Collaborative filtering methods have been applied to many different kinds of data, including sensing and monitoring data, such as in mineral exploration, environmental sensing over large areas or multiple sensors, financial data, such as financial service institutions that integrate many financial sources, or in electronic commerce or web applications where the focus is on user data. The remainder of this discussion focuses on collaborative filtering for user data, although some of the methods and approaches may apply to the other major applications as well. In the newer, narrower sense, collaborative filtering is a method of making automatic predictions, or filtering, about the interest of a user by collecting preferences or taste information from many users, collaborating. The underlying assumption of the collaborative filtering approach: if a person A has the same opinion as person B on an issue, A is more likely to have B's opinion on a different issue, X, than to have the opinion on X of a person chosen randomly. For example, a collaborative filtering recommendation system for television taste could make predictions about which television shows a user should like, given a partial list of that user's taste, likes or dislikes. Please note that these predictions are specific to the user, but use information gleaned from many users. This differs from the simpler approach of giving an average or non-specific score for each item of interest, for example, on its number of votes. The motivation for collaborative filtering comes from the idea that people often get the best recommendations from someone with similar taste to themselves. Collaborative filtering explores techniques for matching people with similar interests and making recommendations on this basis. Collaborative filtering algorithms often require 1. Users' active participation, 2. An easy way to represent users' interest to the system, and 3. Algorithms that are able to match people with similar interests. Typically, the workflow of a collaborative filtering system is: A. User expresses his or her preferences by rating items, books, movies, or CDs on the system. These ratings can be viewed as an approximate representation of the user's interest in the corresponding domain. The system then matches this user's ratings against other users and finds the people with the most similar taste. With similar users, the system recommends items that the similar users have rated highly, but not yet been rated by this user. Presumably, the absence of a rating is often considered the unfamiliarity of an item. A key problem of collaborative filtering is how to combine and weigh the preferences of users' neighbors. Sometimes, users can immediately rate the recommended items. As a result, the system gains an increasingly accurate representation of user preferences over time. Clustering. Clustering algorithms discover structure in collections of data, where no formal structure previously existed. They discover what clusters or groupings naturally occur in data. Examples: finding related news articles, or computer vision, groups of pixels that cohere into objects. Clustering, unsupervised learning. Clustering is also termed as unsupervised learning. In machine learning, the problem of unsupervised learning is that of trying to find hidden structure in unlabeled data. Since the examples given to the learner are unlabeled, there's no error or reward signal to evaluate a potential solution. This distinguishes unsupervised learning from supervised learning and reinforcement learning. Unsupervised learning is closely related to the problem of density estimation in statistics. However, unsupervised learning also encompasses many other techniques that seek to summarize and explain key features of the data. Many methods employed in unsupervised learning are based on data mining methods used to pre-process citation-needed data. Approaches to unsupervised learning. Approaches to unsupervised learning include clustering, in other words, k-means, mixture models, hierarchical clustering, hidden Markov models, blind signal separation using feature extraction techniques for dimensionally reduction, in other words, principal component analysis, independent component analysis, non-negative matrix factorization, and singular value decomposition. Among neural network models, the self-organizing map, or SOM, and adaptive resonance theory, ART, are commonly used unsupervised learning algorithms. Click on each tab to learn more. The SOM is a topographic organization in which nearby locations in the map represent inputs with similar properties. The ART model, ART, allows the number of clusters to vary with problem size and lets the user control the degree of similarity between members of the same clusters by means of a user-defined constant called the vigilance parameter. ART networks are also used for many pattern recognition tasks, such as automatic target recognition and seismic signal processing. The first version of ART was ART-1, developed by Carpenter and Grossberg. Classification. Classification is a form of supervised learning. A classification system takes a set of data records with known labels. It learns how to label new records based on that information. Example: given a set of emails identified as spam or not spam, label them new emails as spam, not spam. Given tumors identified as benign or malignant, classify new tumors. In machine learning and statistics, classification is the problem of identifying to which of a set of categories, subpopulations, a new observation belongs, on the basis of a training set of data containing observations or instances whose category membership is known. The individual observations are analyzed into a set of quantifiable properties, known as various explanatory variables, features, etc. These properties may variously be categorical, in other words A, B, AB, or O for blood type, ordinal, or large, medium, or small, integer valued, the number of occurrences of a part word in an email, or real valued, a measurement of blood pressure. Some algorithms work only in terms of discrete data and require that real valued or integer valued data be discretized into groups, less than 5, between 5 and 10, or greater than 10. An example would be assigned a given email into spam or non-spam classes, or assigning a diagnosis to a given patient as described by observed characteristics of the patient, gender, blood pressure, presence or absence of a certain symptom, etc. An algorithm that implements classification, especially in a concrete implementation, is known as a classifier. The term classifier sometimes also refers to the mathematical function implemented by a classification algorithm that maps input data to a category. In the terminology of machine learning, classification is considered an instance of supervised learning. In other words, learning where a training set of correctly identified observations is available. The corresponding unsupervised procedure is known as clustering, or cluster analysis, and involves grouping data into categories based on some measure of inherent similarity, like the distance between instances, considered as vectors in a multidimensional vector space. Terminology across fields is quite varied. In statistics, where classification is often done with logistic regression or a similar procedure, the properties of observations are termed explanatory variables, or independent variables, regressors, etc., and the categories to be predicted are known as outcomes, which are considered to be possible values of the dependent variable. In machine learning, the observations are often known as instances. The explanatory variables are termed features, grouped into a feature vector, and the possible categories to be predicted are classes. There's also some argument over whether classification methods that do not involve a statistical model can be considered statistical. Other fields may use different terminology, like in community ecology, the term classification normally refers to cluster.